a little, let's compute another very important value of gamma function, namely its modulus of the purely imaginary argument. To find it, we combine the mirror identity with factorial property of the gamma function. Then let's remember that the sign of the purely imaginary argument can be reduced to the sign hyperbolic as follows. Next, we write down the integral representation for the gamma function taken at ix and then at minus ix. We see that the two values are related via the complex conjugation. Plugging in gamma of minus ix into the factorial identity, we immediately obtain the expression for the modulus squared, and then the final expression for the modulus of the gamma function of ix. The next important identity we are going to discuss is the Legendre's duplication formula. Here it is. The full proof of the Legendre's identity is quite cumbersome. It uses complicated double integrals and the non-intuitive change of variables. To avoid this, we opt for simpler and slightly less rigorous proof. We are going to prove it for integer z, and then make an analytic continuation to the whole complex plane. And here we start. First, we write down the gamma function of 2n, which is simply 2n minus 1 factorial. Then we do some work with the factorial itself. We split it into the product of even and odd numbers. First, let's consider an even product. It contains n minus 1 even factors. And as a result, we can factor out n minus 1 twos to get 2 to n minus 1 times n minus 1 factorial. Next, we perform a similar trick with an odd product. There are n odd terms, and we factor out n 2 factors. So instead of 1, we have 1 half. Instead of 3, we have 3 halves. Instead of 5, 5 halves, and so on. The idea here, as before, is to make the product to be comprised of the factors which differ only by 1 from each other. And there is a very nice trick to simplify that kind of products. We multiply and divide it by the gamma function of the first term of the product. In our case, it's 1 half. Now let's look closely at the first two terms. By the factorial property of the gamma function, we can convolute them into the gamma function of 3 halves. Then, since the next term differs just by 1, comes the next convolution of gamma function of 3 halves and 3 halves, which yields the gamma function of 5 halves. Now the pattern is clear. We apply this rule in chain n minus 1 times to get the final term, which is simply gamma function of n minus 1 half, which in turn is convoluted with the last term. And we obtain a very nice reduced expression for the product via gamma functions. Now we may write down the answer for the first n odd terms. Here it is. Next, we collect all the pieces together and plug them into 2n minus 1 factorial, and then into gamma function. Finally, we write gamma function of the double n in the following factorial form. Changing gamma of 1 half to square root of pi, and performing an analytical continuation from discrete set of integers n to continuous z, we recover the duplication formula. Actually, there is a small subtlety here. There exists the following rigorous statement. The analytic continuation from the discrete set to continuous is unique once the initial set has at least one limit point. The set of integer numbers does have the limit point, but it's plus infinity. So our proof is not as rigorous as we would probably like it, but it serves its purpose well enough and suffices for now. Now, let's discuss some more examples of gamma functions applications. Let's compute an integral. First, check the convergence of the integral. We split it into two parts, from minus infinity to 0 and from 0 to plus infinity. Let's investigate the convergence of the second one. The first one is done analogously. The dangerous point is obviously an infinity. So we split the domain of integration into two parts. The first one is convergent, and it is the second one that needs to be checked. To this end, we make the variable change t is equal to x cubed, and change the differential accordingly. This is our transformed integral. Let's integrate it by parts and see what's going to happen. Changing the exponential with its entire derivative, we proceed in the standard way. The first term is finite at infinity. and 1, so there is no problem here. Now let's look at the second one. This one can be easily estimated. Let's focus on its modulus and use the simple fact that the modulus of the integral is always larger than the integral of the modulus. The modulus of imaginary exponential is 1, and we are left with an elementary integral from the power function, which can be now taken yielding the finite answer. Well, you may ask, why did we make integration by parts in the first place? The idea was to raise the power of t in the denominator to make the final elementary integral convergent. Now we are ready to solve the integral itself. To compute, we'll actually need to deform the contour. The problem is that we would like it to reduce to gamma function, which has minus t in the exponential. But we have an inconvenient ix cubed. So let's change the variable accordingly and change minus 1 to e to I pi. Now we put I in the right hand side, and here is the small trick. We add 2 pi in the exponential, which is basically multiplying by 1. We'll use it later. Changing I to e to I pi by 2, we rewrite our changes as follows. Finally, taking cubic root from both parts, we arrive at the final change of x. Let's consider n is equal to 0 case. Suppose t runs from 0 to plus infinity. Let's see what's going to happen with our x. As you see, x became a complex number. It became a ray inclined at angle pi by 6. Now suppose n is equal to 1. Again, t runs from 0 to plus infinity. This time x is a ray inclined at 5 pi by 6. So, utilizing these two changes, we have actually deformed the initial contour, which ran along the real axis, into a sort of bird-wing shape in a complex plane. As you know, we can always deform the contour in a complex analysis as long as the deformation doesn't cross singularities. Notice that our variable t basically plays the role of the modulus of the complex variable on both sides of the contour. Now we are ready to tackle the first and second integrals separately. Let's do the first one. T obviously changes from plus infinity to 0. Next, we interchange the limits and change minus 1 in front of the integral to e to minus I pi. And we notice that the expression under the integral is precisely the gamma function of 1/3. So here is our answer for the first piece. In the same manner, we tackle the second one to obtain the complex conjugate expression. So, summing them up, we finally get the answer. Here we can change double cosine of pi by 6 to square root of 3.